concise statement to the whole story. If G was the symmetry of the theory and H was the symmetry of a solution, so when they were continuous symmetries, we saw that we expect dimension of G mod H, the coset space, which is defined to be dimension of G minus dimension of H. So many massless excitations. Okay. In condensed matter physics, these are also called gapless. These are called gapless excitations. These are general. In other words, if you have particles which you excite, and you find that in the energy momentum thing, you find that you can there is if you want to excite some particle, you don't need any there is no gap. As opposed, if there is a gap, then you have to give energy more than the gap. So suppose so when you are in quantum field theory, you are in a position to create an annihilate particle. So the number of particles is not constant. So if you have a massive particle, you need to actually generate energy. So usually particle and antiparticle are created. So at least the minimum energy you would require to create such an excitation would be 2 mc square, where m is the mass of the particle. But suppose the particle is massless, then you can see that there is no gap. So the scale in the problem is the mass of the excitation. So in this in the example we did was SO2 broken to nothing. We saw that there was the radial mode which had a mass. So the radial mode So, what I have in mind when I am calling it radial is that I think of phi, the field, there were two scalar fields, right. I can define a complex scalar field phi, which is just phi 1 plus I phi 2, and then I can just write phi as mod phi, or if you wish in polar coordinate something like r e power I theta, and then this is the direction which would be the massive direction. And we if you go back and plug into those equations, you would see that the mass square rather of the r field was what we got last time. So, we got something like lambda a square upon 4. Is this correct? I mean, you should look at your notes, or 2, 4 lambda a square. So, I know there was a 4, I do not remember, but 2, 4, whatever, some number times lambda a square. Okay. So, but I really like to think of this as a second derivative, r equal to whatever was the r equal to, I guess the scale in this is a itself, at r equal to a. So, that is what it would be. Okay. And so, for instance, if you want to see this excitation there in quantum field theory, you would say that there is a gap, and the gap is roughly of the order of magnitude, it is lambda a square. Okay. So, this is the difference between gapless excitations and gap. So, if you are in particular, if lambda a square is very, very large, then those excitations would never compared to the energy scales of your problem, you would not look at those excitations, you would only look at things like this. Okay. So, there is terminology difference between fields. So, particle physics people will say massless excitations, and condensed matter people would say gapless. They are really the same thing. And there was a question after class or towards the end of last lecture, which said, I was very clever in choosing a parametrization. I wrote something like this. I wrote, let us write, we started out with something like 0 a, and then I said I will write eta, and I wrote e power I theta. So, we worked out as eta and theta were excited, I mean these things, and The claim was that this, so this theta will map to exactly this theta, you can check, and R will become just A plus eta in this setup. Okay. And yeah, so the thing is there a clever way of parameterizing it? The answer is yes, and in general you could. So H is a symmetry of the solution. So what you would do is, so you are given H, which is a subgroup of G, and we will assume that they are all Lie groups. So in the fact that everything can be written as exponential of something. So what you would do really is all elements of H. So typical group element, you would write H as some e power. We will see something, it can be written something like this, thetas A's and T A's. So A's would be as many as the dimension of H, that means that many parameters. So if it were SO3, it would be 3 parameters and some sort of generators. We will see that we can write it in such a form. Okay, and the remaining stuff you could write in again in this thing. But the key point here is that you can see that I am not working for lowest order in theta or anything. It is true to all orders in theta. If you write it in this clever fashion, you can see that it is true to all orders in theta, or you just look at it in a global way. Again, you would see that this is true to all orders. It is not just saying that the mass the quadratic term is 0. It is saying that all terms there is no potential. Okay. And so there is, so in other words, I just want you to remember that there exists clever or okay, let us leave it at that, parametrizations, okay, that explicitly show masslessness to all orders. Okay. So, but so we have been discussing classical field theories, but you can ask what happens in quantum field theory, and there is something important which comes. Okay. So, what happens, I know this is not a QFT course, but nevertheless the result is something which you can remember. Okay. And so first thing is by that I mean what happens to Goldstone's theorem, and we will see that there is a dimensionality dependence in the story. Okay. And so first so the first point to remember is I keep using classical vacuum solutions, but the analog of that in quantum mechanics or quantum field theory is a classical vacuum. Is there a question? So vacuum is the ground state, what we will call the ground state, and usually you use a symbol something like this. Okay. So that is the first point. The second thing is to ask can there be what happens to spontaneous symmetry breaking or Goldstone's theorem. So first let us consider discrete symmetries. In quantum mechanics, this is something which if you have done a course in quantum mechanics you will know about. So for instance, suppose you have a simple potential in quantum mechanics, again a double well kind of thing, okay, and say plus A and minus A, and let us say there is a Z2 symmetry which is takes x goes to minus x. So the potential has a symmetry in the theory, etc. But the thing is, so and let us say let us call this generator H. So the question is H equal 0 not equal to 0. Okay. So this would be the analogous state. Right now I am just getting to the point of stating what I mean. So by this, so only then we would say the symmetry is broken. If H acting on this thing is 0, that means its symmetry is it's a symmetry of the theory. Okay. So this is just a statement that it is. So naively you would think, yeah, the first, I mean first guess is yes, I mean equal to 0. Okay. So in terms of the wave function, it's a wave function symmetric. Is if you want to think of that, you say psi ground state of x, is it equal to, up to some phases it might, I mean I will permit phases, that is not so. So is this, so x goes to minus x, this is what I mean. Okay. So H is the generator, so yeah, this is not correct. So I should write something like this. So H, now it's, I think it makes sense. Okay. Why should it be 0? Yeah, tell me. Yeah, so it should map. So all I am saying is H maps the 0 vector to 0. Not, I mean it's not 0. 0 is different from the vacuum. Okay. So what it could have done is it could have done the following thing. It could have taken H of 0, could go to say some other state. Okay, and then H of 1 could be equal to 0. Here is, okay. So if it's a symmetry of the thing, it would it will take it to itself. No, that's what yeah, it is proportional is what I wrote, that's what I am saying. No, it should give the vacuum. You do the following thing, operate on a, so H is a discrete symmetry, H square is identity. Okay. So a trivial way to check, I mean to sort out my error, for instance, is to act with H square. So if I did it this way, okay, so the proportionality I put here is because it could be minus of it, does not matter. Okay. But okay, so now the key point here is what is the ground state. So this is the kind of thing I want. So these two are the same statement. Okay. So we know that the true, so you might that the true ground state of this theory is indeed is actually has no such, this thing cannot happen. If this happens, we would say it's we would say that symmetry is broken. Okay. So roughly what one has in mind is some wave function which supported this well, that is the naive guess, first guess, and the second guess is one more here. So there are two degenerate vacua, this is what you would think. Okay. But quantum mechanics, you know, this does not happen because there is something called tunneling. So because of tunneling, okay, you find that the actual true ground state is a coherent superposition of the two states which you have written in some ways. Okay. So the true ground state actually preserves the symmetry. So the conclusion is that there is no, so just based on tunneling arguments, breaking of of a discrete symmetry in quantum mechanics. Okay. By the way, we can also, it is useful to think of quantum mechanics as 0 plus 1 dimensional field theory. It has time, but it has a discrete number of degrees of freedom, countable or whatever. So you just call it 0, because if you have if you say one dimension, it has one field worth of, there are no fields in the theory. So it is best to think of it as 0 plus 1 dimensional CFT. This is just a trivial way of stating it, but because it will connect up beautifully with everything else. Okay. So similarly, since we are saying this would be 0 plus 1 dimensional, quantum mechanics is nothing but 0 plus 1 dimensional quantum field theory. Okay. So now the question is, let us go to, let us raise the thing to one extra dimension. So let us go to 1 plus 1. What happens in 1 plus 1? Okay. So, now we have infinite degrees of freedom phi of x, and let us say that we chose phi of x to be equal to whatever is that web which breaks. It is again exactly like this. So, instead of the, so I just said the field takes values say plus a or minus a. I again have a discrete Z2 symmetry, okay, and the symmetry of course H takes phi 2 minus phi. Okay. So, this is one ground state, and phi 2 of x equal to minus a is the other ground state. This is an example we have looked at in the last lecture. So, what the question here is, now suppose I prepare the system in this state. I could have done the same thing in quantum mechanics. I can start with an initial configuration which where the particle is localized at this well, choose a wave packet which is localized there, okay, and then but you can show that after some time there is a finite non-zero probability because of tunneling, and that shows you that the true ground state is indeed something else, okay. So, I am doing the analog of that. I am saying let me go ahead and prepare the system in this first ground state. So, put all the field in the everything everywhere it is at A in all of space. So, now the question is, can it tunnel? Okay. Now, the point here is, if it has to go to the other ground state, what you require is sort of spontaneously everywhere it has to tunnel and go in one fell swoop to the other thing. If it went only in some region, we know that it will be like the kink or whatever. Okay. So, this sort of I am not giving you a proof of anything because we are not doing quantum field theory. I just want to give you an intuitive feel of things. What this tells you is that that cannot happen, because the one more thing you have to remember is that the tunneling probability is actually fairly exponentially suppressed, but now given that it has depends on the height of the potential, but it also now you have to do it everywhere in space. So, it more or less it becomes more and more unlikely and improbable, okay. So, the point is that in any field theory other than quantum mechanics, actually discrete symmetries can be spontaneously broken, okay. So, really tunneling has probability tending to 0. So, if you discretize the thing, you will see that you require some bunch of things, but if you take the continuum limit, you are gone, you get 0, okay. So, this theorem was actually originally developed in the context of statistical mechanical systems by Mermin and Wagner. So, it is called the Mermin-Wagner theorem, and it was adapted in the context of quantum field theory by Coleman. So, let us call it the Mermin-Wagner-Coleman theorem. Okay. Most textbooks call it the Mermin-Wagner theorem. So, what it says is that in dimensions in dimension when the dimension of space time is greater than 1, spontaneous breakdown of symmetry okay. So, just one in the context of stat mech systems. So, the analog of dimension becoming greater, space time becoming is like, for instance, the 2 dimensionalizing model. Those of you know that the critical temperature is at a finite value, but for the one dimensional the Ising chain, the critical temperature is 0, which basically tells you that there is no phase where actually symmetry is broken. You can go up to 0, okay. So, this is for of discrete symmetries, but they also have something to say about continuous symmetries. Now for me it's I mean we cannot use arguments like tunneling. You can see that there are subtleties, because if you have a continuous symmetry I can smoothly change things. Okay, so there is a little bit more freedom. So the question is not, I mean one should not use these kind of hand waving arguments. Even this I think is hand waving. Yeah, I mean the setting is completely off, but because we are doing classical field theory I just wanted to give you an intuition. For continuous symmetries the statement is that you require dimensionality of space time to be greater than or greater than 2 for continuous symmetries. So in 1 plus 1 dimensions, for instance, you cannot have a continuous symmetry. So now you can see the change here for continuous symmetries, you go from 1 to 2, spontaneous, of symmetry of continuous symmetries is possible. It is usually written in a negative way. It says that for dimension, so one says that the critical dimension for this is 1 or 2. This is another way of saying. Okay, is this clear? Okay. So many of the considerations that we are going to look at, you should remember that these are the issues, okay, and this is worth memorizing. So what I am going to do now is to this is all I have to say about Goldstone's theorem. The next step is to actually understand how to convert. So we have here so far we have been discussing global symmetries. What will happen if you want your symmetry to become local? Okay. So in other words, so when we let us be more specific, let us consider the simple example of SO2, and so I think I should write from left to right, not from right to left. Spacings get messed up. I am going to introduce some parameter which I call Q. Become pretty soon clear what I mean. Okay. So this is just some SO2 global symmetry with the parameter theta I have written as Q times alpha. Okay. And alpha is supposed to be an angle, and alpha is identified with alpha plus 2 pi. Okay. So now you can, and Q is some integer which I will call charge. Okay. If you have just one scalar in your theory, I do not think it is a big deal what this Q means. You can always say fine, I mean I live with I could have redefined it and defined Q alpha as theta, but suppose you have the same SO2 acting on two different fields. So I could have one field which has Q equal to plus 1, I can have some other field which has Q equal to 2, then there is a distinction. It means that in field space when one of them is rotated by 2 pi, the other is rotated by 4 pi. Okay. So we will call Q the charge. We will see that this relates to charge in a physical setting. We know that charge is quantized, etc. Okay. So this will map to something like that. Okay. So right now alpha is global, is a so rather so we have a, what we have is we have SO2 global symmetry. Okay, and let us assume that we have some Lagrange density which is a function of phi I and d mu of phi I, okay, such that SO2 is symmetric. Okay. By global I mean its alpha is just a constant, it does not depend on space time. Okay. So now yeah, remember I also told you some time back that there is a way of breaking SO2 to some ZQ or Z and some discrete group. Suppose we have such a field phi 1 phi 2 such that they pick up a wave and you have breaking of symmetry SO2, but now you can see that there are rotations. So, yeah, let us assume let us assume that suppose we will come back to the local part. I just have a comment to make about the goals. We have a spontaneous breakdown of symmetry of SO2 by the fields by say something like this phi 1 square plus phi 2 square, getting a wave, we will call it A square. Okay. So, this breaks. So, you could start by like we did last time, we could say phi 2 equal to A, but now we can ask what is the what is the symmetry of. So, let us choose phi. So, let us choose this like we did last time and ask what is the symmetry of this, the unbroken symmetry. Okay. So, obviously, the SO1 is nothing, but you can see that I can make rotations of pi. If q is 2, okay, then I can make a rotation by 2 pi over 2, which is pi, such that this will still be identity, because there is a 2 in this transformation. More generally, if it is q, you can see that if I mean SO2 is broken down to the subgroup ZQ, which is just rotations with angle 2 pi over q. Okay. So, now H is actually ZQ, which is rotations by okay. So, this I would say that this situation where G is SO2 and H is ZQ, but of course, Goldstone's theorem will still say that there is one Goldstone boson, because in terms of continuous counting this is still 0, the dimension of this continuous dimension is 0. Okay. It of course has certain elements. Okay. So, this is so now the idea is, can we so now we will can we obtain a Lagrangian density that is invariant under local SO2 transformation. Okay. So, what I mean by that is just go back and think of the alpha parameter as a function of space time. Okay. And let us go back to the Lagrangian density and look at it. So, you were given that this looks like something like this. U, which is a function of phi 1 square plus phi 2 square. Okay. So, first step is to, so what we will do is we look at first so what has, so now we just go back to the same transformation and ask what happens if we look at the excuse me, the one with phi prime, but alpha now dependent on x. Okay. Easy to see that the potential energy this is easy to see, because it does not matter, it did not really matter where, it just depends on the combination phi 1 square. But what about this guy? Okay, now it is no longer invariant, and what I am going to do now is to make a slight change in notation, which is to go to a complex. I will go work with complex fields, which rather than real, just for convenience, and you will see. So, let us define phi to be phi 1 plus and define phi star or phi bar as minus I phi 2, and I need to write out how this transforms. And so, you can see that phi prime would be phi 1 prime plus I phi 2 prime, and we put things together. So, that this will be phi 1 prime is cosine phi 1 plus sine phi 2, plus I times okay. This may look very complicated, but actually this is nothing but okay. So, phi prime just so it is like going to the eigenbasis of this, I am diagonalizing this matrix if you wish, and so phi prime is e power I q alpha again okay. And just looking at this thing, we will say that phi the field phi has charge plus q and the field phi bar as charge minus q. Okay. So, in quantum field theory we will see that these are like particle antiparticle things. So, electron and positron, if this were fermionic, these are bosonic, but does not matter. I mean what I mean by that is that they will have opposite charges, okay. And I can rewrite this Lagrangian in the following fashion. Okay. So far I have done nothing, I have just rewritten in terms of a complex basis. Okay. Now the thing we will see is that we will see we will address the question whether the kinetic energy is independent, is invariant under this. Okay. So, for that what I will do is I will look at only one of these pieces, but I could have done it in real things in using phi 1 and phi 2, it is a little bit messier, okay. But you do not have to feel bad about it, you can go home and work it out. Okay. So, what I want to know is what does d mu of phi prime look like. Okay. So, I mean so yeah, let us do this. So, d mu of phi prime will be e power I q alpha phi, and alpha is also a function of x. So, now the derivative can act on two things. Okay. So, you can see if alpha were independent of a constant, this term will drop out and this is transforming nicely, it is just transforming like exactly like phi, and it is not hard to see how it will be similar to this, except there will be a minus sign coming out here. Okay. So, again now you can see that this product will, when alpha is independent, is a constant, only these two terms, and there is a nice cancellation. Okay. So, the offending pieces are out here, these two guys, and we see that it is not invariant, okay, it is to be expected once you make things local, the things which involve spatial derivatives should not work out, the cancellations which happen should not work out. Okay. And but you could take two lines of thought. One would be to say, fine, why I do not care about local gauge transformations, I will only work with global things, and that would be the end of the discussion. But there is something very interesting which comes by saying that no, I want to make things invariant, I want to make it locally invariant. Okay. And so again there are many ways of doing it, but there is something called a minimal way. Okay. So what we will say, prescription. Okay. So this means that it is just a way of doing it. Okay. So minimal prescription to make Okay. So again I do not have to prove anything, I just have to tell you the prescription, and you can go and check that it is global, I mean it is invariant under local. Okay. And the prescription is very simple. So if you have a whole bunch of fields, so you have phi and the mu of phi, the prescription is very simple. You change what you mean by derivative, you introduce some new derivative. Okay. Okay, so this is some new derivative. Okay, and we will call it the covariant derivative. Okay. And the condition, the requirement is that, so here the problem was with these derivatives. I will just postulate this, we will work out what properties we need, and then I will construct that object for you. Okay. So this is what will happen, the mu of phi prime, I will put a prime even on top of this, you will see why, but if you do not put the prime right now I will forgive you for that. That means it transforms nicely, if I mean that is what that would have been our wish, but alpha here remains local, I am not making it. Okay. And of course the same covariant derivative acting on phi bar should do the same thing. Okay. Now you can see that if my covariant derivative satisfied this condition, trivially it is invariant and life becomes good. Okay. So now we will see how this is done, but before that we should it is useful to go back to the days of Leibniz. By the way, two people invented calculus, one of them was Newton, who was the other? Leibniz. Okay. And most of the notation that we use today is due to Leibniz, except in physics courses. Okay. So derivatives in I use this in this course all the time, which is dot for derivatives, right, dot, double dot, triple dot, so on and so forth. So that was the notation which was used by Newton, which was very useful because he was trying to solve problems in mechanics by inventing calculus, but most of the notation that we use today is modern notation is due to Leibniz. Okay. So there is an important rule called the Leibniz rule, and is this the correct spelling? EI, right, Leibniz. Again there is no universality, I see a T put here. So Leibniz rule, which is an important rule for derivatives, and which says the following: if you have two functions, so let us just do simple. Okay. So this is the important rule, and whatever derivative we create here, that better satisfy this rule. This is true for one variable, it is also true in multivariate calculus. So, so here these derivatives are multivariable d plus 1 variables. So, this is the kind of thing that you expect, okay. But so this is a property. So, this will be satisfied by this rule. So, actually yeah, so let us write it this way. Okay. And the rule will be just replace these by the covariant derivatives. This rule will be satisfied by d mu as well. Okay. So, that is why it has a right to be called a derivative. This property is called a derivation. Okay. So, the derivation property is something satisfied by this thing, but it gives up one interesting property, which is however, we know that if you have smooth functions, the order of taking derivatives does not matter for smooth functions, okay. But so I can rewrite this in a slightly different fashion. I can write it as a commutator of d mu, and d nu acting on f is 0. It is just the same statement, but I just took this to the left hand side, okay. So in other words, we say that so we say that normal derivatives commute, okay, and the key point is covariant derivatives do not commute, do not necessarily commute, they may commute, okay. Need not commute. So, by that we mean something like this: d mu d nu acting on some field phi need not be 0. Okay. In other words, there is an obstruction to commutativity. Okay. So, the obstruction is actually interesting. Okay. So, I have not, we will see what this obstruction is, it will turn out to be something which we know, okay. And we will see that this way of defining things will be generalizes beautifully. Some of you have done general theory of relativity, you would have seen something like this out there as well, okay. So, what is happening is that the covariant derivative does one thing for you, it makes your fields transform nicely, it removes that horrible derivative piece out there, and next bit is that it satisfies the derivation rule, but does not satisfy the commutative rule. These are the things. So, let us now implement the prescription. So, what we will do is postulate the existence of a new field okay, and this field is a vector field, okay. So, it is a vector valued object, okay, that transforms under local SO2 as delta A mu okay, this is how it changes, okay. So, by this I mean Okay. And since this coordinate this thing does not act, the SO2 does not act on space time fields, the argument is still the same. So, there is no worry about delta, delta bar, all of them are the same. Okay. So, this is just a postulate. Okay. Now, you can see that this guy has just about the right thing to remove something like this. So, I will, so let me define so this is just definition. Okay. So, there is a way to read this. It says that if phi was a field which had charge q, okay, then you put it in the, so the charge q comes this way. Now, you can ask phi bar, what was the charge of phi bar? Minus q. So, it acts differently. Suppose there was a field which was which did not transform under this, there was charge q equal to 0, then there was no need to, it does not transform under this thing. So, there is nothing to be done. So, when charge is 0, the covariant derivative reduces to your normal derivative. So, it only sees fields which transform under this symmetry. Okay. So, now it is a trivial exercise to go back, maybe we will look at it next lecture, is to go back and see that this is precisely this minus sign which I have put here, I think it is correct. Okay. So, you can see that when I do this, the delta of this object will get one extra piece which would be d mu alpha with a minus iq d mu alpha phi, which is exactly what I have here, it will cancel it. So, I have adjusted, I have just chosen it in such a manner such that it transforms like this. Okay. Maybe I will do it, since I have a couple of minutes, let me just do that. So, now this primes will come into play, I put a prime because a also changes, it is not like a does not change. So, d mu prime of phi prime, now we just look at the definition there, d mu of phi prime minus I q a mu prime phi prime. So, now I have to use all these things. Okay. So, now I can go ahead and collect terms together. So, d mu acting on phi will give me e power I q alpha d mu of phi. I can combine it with this piece and I can rewrite this as, now what remains I have to write out, one part is when the d mu acts on this, okay, and this piece which was left over. So, these two cancel out. Okay. So, you can see that I have achieved what I wanted, and before I finish I just want to point out, if you see you should see some familiar something similar to what you would have seen for the electromagnetic field. This is how it transforms under what we call gauge transformations. Okay. So, just a comment is that similar to the transformation of the electromagnetic vector field, 4 vector field. Okay. And there are instances in which you can't I mean, and in fact you can think of electromagnetism as related to a SO2 or a U1 internal symmetry which is local. Okay. So, I am not saying this particular thing has to be, there could be many other symmetries in nature, not everything has to be electromagnetism. So, but it could be thought of as electromagnetism. Okay. So, next time we will go back and look at the structure of all the terms. So, now we have already achieved what we set out to do, which is we know what to do, okay. And maybe before we meet next time I recommend that you check what you get on this side. Okay. And there are and Leibniz rule is very interesting. So, let us consider an object like you know what should be d mu of phi square, okay. You work out these two things. So, one, let us look on this phi square, what would be the charge of something which is like phi square? 2q, right. What about an object like this phi bar is 0, okay. So, according to this I am just looking at the charges and saying that how did it go with a minus sign, 2iq a mu of phi square, and this should be just ordinary derivative of phi bar. Okay. So, it is fun exercise to check that I can make Leibniz rule work, and it will be compatible with these two statements. That is because the covariant derivative does depend on the charge of the object on which it acts, it is very important. So, use Leibniz rule and check that this is indeed true, that is one thing, and check that it does not commute and work out what this is. This is fun, I mean I will work it out next class, but it is going to be boring if you have not worked it out, you should see something familiar. Okay. So, we will continue there. Next lecture we will work out what these things are, the abstraction to commutativity, and then we will proceed from there.